Building on quantum mechanics, let's now talk about how to write electron configurations. So when we write electron configurations or draw orbital diagrams, we're going to do so by going through this together using your energy level diagram. You should have that in front of you right now. And I'm going to write our electron configurations here and my orbital diagrams off to the side. I think you'll find that after a bit, after you've seen a couple of examples, that we won't have to draw all the orbital diagrams for all of them. I think that the point will be made, but we'll do them for the first few. So let's draw the orbital diagrams first. And in order to do that, you always have to know the number of electrons. When we are trying to figure out the number of electrons, we go by the atomic number, which in our full or complete elemental symbol will be the bottom number. So in this particular case for hydrogen, it has 1 electron. When we start on your energy level diagram, what we said before is that you always go from the lowest energy level first, which always will be your 1s orbital. In order to hold electrons, you can have 2 electrons, but one must spin up, have a positive half spin. The other one on the other side has to spin down, have a negative half spin. Mathematically, we always start with the positive, so because I only need 1 electron, I'll draw a single up arrow. Now, an older convention is to draw a single circle and a slash to represent the electron. If you needed then a pair of electrons, you would do a slash in the opposite direction, creating an X. Now when we write the electron configuration, all we do is write the orbitals that were used and how many fit into each one. So for this one, we started with the 1s orbital, and we placed 1 electron into it. Adding up those superscripted numbers, you would be able to figure out how many electrons you've used so far if you were using or producing one for iron or something much larger like bromine. Let's try lithium. Again, the first thing we need to do is figure out how many electrons it can hold. In this case, 3. We always start at the lowest position on the periodic or on our energy level diagram, which is our 1s orbital. In this case, like in all cases actually, that first s orbital can hold 2 electrons, one spinning up and one spinning down. The question for you is, well, is that enough electrons? No. So we need to go on to the next lowest energy level diagram, or orbital on the diagram, which is the 2s. We have only 1 more electron we need to place, so it can fit into that orbital as a single up-spinning 2s electron. Now writing out the electron configuration, just like last time, we say how many electrons were placed in each orbital. So in the first 1s orbital, we placed 2. In the second 2s orbital, we only needed to place 1. Again, if you're trying to keep track, we just add these numbers together to tell us the number of electrons. Moving on to oxygen, and I think this is probably the last one that we'll need to write or draw the orbital diagram for, because I think people will get the point of this. We're going to look, and it has 8 electrons. On our energy level diagram, we always start with the lowest energy orbital, which again is always a 1s. It can hold 2 electrons, one that spins up and one that spins down. Is that enough electrons? Well, no. So now we need to go up the energy level diagram. The next lowest orbital is the 2s. And it again can hold 2 electrons, one that spins up and one that spins down. Now progressing up the energy level diagram, we can see that at the second energy level there's also room for 3 2p orbitals. Now unfortunately those 2p orbitals, sometimes people get thrown off about them and they're like, oh, how many electrons? Remember, every circle represents an orbital. Every orbital can hold 2. Now, before we start to fill it, I want to ask you a question. What do we know about all electrons? Well, all electrons are negative. Do negatives like to be together? No. So when we're filling these 2p orbitals, we place them as far apart as possible, placing one electron into each orbital first, and then we pair them if we have to. So I'll place one in the 2p, another one in a single 2p, another one in a 2p, and notice now we need one more electron, so I have to create one pair. It's not correct to have one empty 2p and have two pairs of electrons. All electrons are negative. We want to separate them as much as possible. When you're drawing out this diagram, you would draw it all in a single line with spaces in between the types of orbitals. Unfortunately, I didn't have enough space on my screen, and that's why it flipped down onto a second line. So writing out the electron configuration. We started with the 1s orbitals, and it held 2. Then we went on to the 2s orbitals, and it held 2. Then we went on to the 2p, and it held 4. Notice 2 plus 2 plus 4 gives us 8, the number of electrons we were hoping for oxygen. I think we're going to skip over fluorine because we can get the point for that one. But for neon, we're going to do this again, and just using the electron configuration. So make sure you have your energy level diagram in front of you. The lowest energy orbital is always the 1s. And how many electrons can it hold? 2. Is that enough electrons? No, well, because neon needs 10. In the second energy level, let's just change the color here so it's very clear. In the second energy level, the first orbital that I hit is the 2s. Notice the s are the simplest ones, so they're the lowest energy at any given distance. It can hold 2 electrons. Now we still don't have enough because I need 6 more, so I continue on to the 2p's. Those 2p's, those 3 2p orbitals can hold 6, the number we needed to use. Now just to highlight something for you, notice we had one 1s orbital, which held 2 electrons. At the second energy level, we had room for 8 electrons. Does that remind you of anything? Well, yeah, this reminds us of the Bohr model, the 288 idea. So this actually explains for us, well, why is the Bohr model 288? You were probably told in some previous course, well, just because, or, oh, it's too much for this particular course. Well, this is why. It's based on quantum mechanics. So let's continue on now and look at potassium. So potassium, we start out, like always, with the 1s. How many electrons can it hold? 2. Changing color so that we've got the second energy level in a different color. Let's move on. Then we move on and we hit the 2s. How many can it hold? 2. Is that enough? Well, no. So far we've only dealt with 4 electrons. So I move on to the 2p. And it can hold a maximum of 6. That gives us 10 electrons so far. Is that enough? No. So now for the first time we have to move on to the third energy level, the 3s. And the 3s, like every other s orbital, can hold 2 electrons. That gives us 12. Is that enough? No, we need 19. So we need to continue on. So we go to the 3p. And how many can it hold? 3 orbitals, 2 each, so it can hold 6. That gets us to 18. Now this is where I want you to take a quick, careful look at your energy level diagram. What is the next lowest energy level on the chart? Well, it's not the 4s, it's not the 3d, it's the 4s. Even though the 3 is closer to the nucleus, it's so much more complicated in shape that it gets passed in energy, and we put that one extra electron we need into the 4s. Okay, last one that we're going to do together, we see, is the iron, which has 26 electrons. I'm going to run through this a little more quickly because I think that most people have caught on to this point by now. If you haven't, please make sure you come in and get some extra help from me. So, we start with the 1s, and it can hold 2. That's only 2 electrons, so that's not enough. So I move on to the 2s, which again can hold 2, giving me 4. Not enough. So I move on to the 2p, which can hold 6. Not enough. So I move on. Now I'm up to 10. Then I move on to the 3s, which can hold 2, giving me 12. Not enough. So I move on to the 3p, which now can hold 6, giving me 18. Still not enough. So, looking at my energy level diagram, just like for potassium, I look at the chart and I see that the next lowest energy level is the 4s. But what I told you at the end of the quantum mechanics presentation is that I want all the ones with the same number grouped together. So although I have to fill the 4s first, I want you to leave yourself a little space here that's available in case I need to use it for the 3D. So I'm going to put my 2 electrons in and count, and oh look, that's only 20 electrons. So now in fact I do have to go back to the 3D and I need to put 6 electrons in where I could hold a maximum of 10. That's important because remember the 1, the 2, the 3, the 4 represents our distance. Remember, this is not the way your textbook is going to present it, but it is how I want you to write it. Now, why is it that this is happening? What we see is that the 3D are closer to the nucleus than the next highest s orbital. But remember, there's a balancing act here between the distance from the nucleus and the complexity of the shape. And what we see is that the 3D are so much more complicated than the 4s that even though they're closer to the nucleus, the 4s is lower in energy. That's why they're positioned above the s on the energy level diagram. So after the 4s orbital is filled, the next electron goes into the 3D. Because the 3D is closer to the nucleus, we call this backfilling, as an orbital closer to the nucleus is filled after one further away. When we look at our textbook, as I've said to you a couple of times, that we will see the textbook write electron configurations in the order that the orbital is filled. However, I want you to write them based on the principal quantum number, the 1, the 2, the 3. That is, all the orbitals with the same principal quantum number are written together. That's because it's the outermost electrons that contribute the most to the properties of an element, so those are the ones that we want written last. Also, what we see is that when we form ions, it's the outermost orbital electrons that will be removed first. So it's advantageous for us to have those electrons written at the end so that we are cleared to steal them first. So we've already looked at iron, but let's quickly write out the electron configuration for bromine so that you can see how this plays out. So I start with getting 35 electrons in total. I start with the 1s holding 2. Moving on to the second energy level, I hit the 2s, which can hold 2. Going on still in the second energy level to the 2p, it can hold 6. Continuing on to the third energy level, the 3s can hold 2. The 3p can hold 6. I'm going to leave myself some space for my 3D in case I need to use it and fill my 4s, which is 2. That gives me 20. Now I go back and I do in fact need to use my 3D, which can hold 10, giving me 30. And now I move on to the 4p. It can hold a maximum of 6, and I'm going to place 5 there. You're going to do a lot of practice on using this particular set of skills in class because it's really important that you're confident in it before we look at how to twist that up and do shortcuts. For those of you that have already worked through the practice, the next day's video will show you a shorthand method that you can use when you're asked to do so.